Hey guys, what's up? Today we are looking at doing something a little bit different. I'm going to go through a proof from real analysis where we would prove that a sequence is Cauchy. And we could do this by showing that the sequence converges and therefore is Cauchy, but what we're actually going to do is we're going to show that it's Cauchy using the definition. So what does the definition of a Cauchy sequence mean? A sequence A sub n is Cauchy if and only if for every epsilon greater than 0, there is a capital N in the natural numbers such that once we pass up capital N with m and n, then the sequence terms an minus am absolute value are less than epsilon. So basically at some point there's a threshold for epsilon such that when you pass up that threshold, capital N, the sequence terms are just arbitrarily close together, no matter which two terms you pick. So that's the definition. We're going to try to show that this sequence satisfies this definition. So as with any good real analysis proof, we're going to start off with the final estimate and kind of work our way backward and see which capital N we need to choose based off of that epsilon. So we're going to let epsilon be greater than 0, of course, and then we're going to start with the final estimate. So this would be an right here, and this would be am. So basically I just take my sequence and plug in little n and little m. Then I'm just going to find a common denominator here. So just go ahead and find a common denominator, multiply top and bottom by 3m over 1, 3m minus 1 here, and then multiply top and bottom by 3n minus 1 over here on the right. So just do a little algebra, simplify this down. Go ahead and distribute that numerator on both sides. So once we distribute this out, we can actually cancel the 6mn with the 6mn, the negative 1 with the negative 1, and we're left with a 5m because we have 3m minus negative 2m, so that's 5m, and negative 2n minus 3n is negative 5n. So 5m minus 5n. Now we're going to just go ahead and take that 5 out of the numerator, and I'm going to try to cancel 3m minus 1 and 3n minus 1, and to do that I'm going to have to add and subtract some things. So I have a little bit of a strategy. Here's where the proofy part comes in. It's being creative and starting to add 0 and stuff like that. So basically what I'm going to do to get a 3m minus 1 to cancel, I need to add 2m, which means I have to subtract 2m. And then to get the minus 1, I also have to add 1. So I do a little bit of addition here just to simplify things. 3m minus 1, the rest is negative 2m plus 1 minus n. Now I can split off that first term and cancel this 3m minus 1 and this 3m minus 1. Everything else stays over here off to the right. Then, so once I cancel that term, I just have 1 over 3 little n minus 1. Then I'm going to pretty much try to do the same thing over here, but now with 3n minus 1. So I'm going to take this term on the right, add and subtract. I'm just going to go ahead and add a 3n and subtract a 3n, and then I'm going to subtract a 1 and add a 1. So I can write this as 3n minus 1 over here on the right, and then the rest is left in the middle as negative 2m minus 4n plus 2. So now I can split that last term off and cancel that 3n minus 1 and leave me with 1 over 3m minus 1. Now this is really the whole purpose in doing that, not just to make the denominator simpler because two denominators are really more complicated than one. Our whole purpose in doing that is to cancel or remove this term because the numerator is always going to be negative. The numerator is negative here because this m and n are always greater than 1. So I can just say the numerator is negative. If I drop that term, it can only get larger. So I'll drop that term and I'll say, okay, this is 5 times 1 over 3n minus 1 plus 1 over 3m minus 1. Now I can use the triangular inequality to split that off. And now I can focus on some much simpler terms. Now these feel a lot more like regular real analysis. So if I can just make both of these terms less than some sort of epsilon, make it work out to be epsilon at the end, then I'm good to go. Probably what I should do is make both of these less than epsilon over 10. Because I have a 5 multiplied onto each one. So just make both of those less than epsilon over 10. How can we do that? We can do that if we make it work for capital N, because capital or little m and little n are both greater than capital N. The reciprocal, if I stick little m and little n in the denominator, it's going to be less than 1 over capital N. So 1 over little 3m minus 1 will be less than 1 over 3 capital N minus 1. So we're good to go if we can make this work out. Well, how do we make this inequality work out? Well, we just solve for capital N in that inequality. So we can do that if we just multiply both sides by 3n minus 1, and then multiply both sides by the reciprocal of epsilon over 10, which is 10 over epsilon. Then solve for capital N by adding 1 to both sides, and then divide by 3 on both sides. And that's the capital N that we need to choose at the beginning of the proof. Now we can go back and actually do the proof start to finish. So you say let epsilon be greater than 0 and let capital N be greater than this number. I can guarantee capital N exists by the Archimedean property. The Archimedean property tells me for any real number, in particular 10 over epsilon plus 1 over 3, I can find a natural number larger than that real number. So after that, we basically just go through and we say, okay, an minus am, just write it out, and then go through the exact same steps we had before. Find the common denominator here and here, multiply out the numerators, cancel the terms, take the 5 out, add and subtract 2m, add and subtract 1, simplify the terms, break off the first one, add and subtract in the second term 3n and 1, and then simplify it down, cancel the 1 over or 3n minus 1 over 3n minus 1, drop the middle term because it's negative, then use the triangular inequality. Now I know both of these are going to be less than epsilon over 10. 5 times epsilon over 10 is epsilon halves. Epsilon halves plus epsilon halves is epsilon. So what have we done? We've shown that for all epsilon greater than 0, there exists a capital N. Ooh, I should say for all, or I should say let little n and little m be greater than capital N. So that is a slight modification I need to make this completely solid. But then we have a sub n minus a sub m is less than epsilon. So that is obviously much less efficient than just showing that the sequence converges. So that would be easier to show that it's Cauchy. But if you just want a challenge, it's very algebraic. It's very computational. It's almost like just doing, algebra. And so it's fun to me. I think it's a good problem, a good way to understand, to just kind of test your proof abilities, trying to work with Cauchy sequences and stuff like that. So thanks for watching. I'll see you next time.